So welcome everybody who made it to Introduction to Computer Graphics camera lecture. So it's not only about cameras, but mostly, and yeah, I hope I get you down to earth with the view space and the configuration of cameras, as they're actually very important for most of the Yeah, I totally have to find the other screen. As always, the sources are the basic book of Sanjay Madhav, then the classical real-time rendering, and the classical computer graphics book. So, cameras, I hope you've heard it already, but if not, repeat it. There are typical ways to do the projection: the orthographic projection and the perspective projection. So you can easily distinguish between them. One looks like Diablo and one looks like the real world. That's just kind of a bridge you can build in your memory. But the orthographic projection is using a view cube. So you're looking into a cube, all the view lines are parallel. That also means that parallel lines stay parallel, just like Diablo, where items that are farther away do not appear smaller. That's the whole idea. Why would you use an orthographic? Of course, there's a whole genre using them. But also if you do a 2D game and try to make it look nice, but still do it in look 2D, but still do it in 3D, then you typically use an orthographic camera. So that is a very, very common setup. And sometimes the 2D engines built into 3D engines actually do that for you. So you're using it anyway if you're creating a 2D platform. The perspective projection uses a view frustum, which is pyramid where you cut off the head, basically. Parallel lines stay not longer parallel, but what actually happens is that nearer objects appear larger and farther away objects appear smaller, relatively. And also you have these points where all the lines converge, like you look at long street and then the street ends up in a single point. That's typical active. We see with our eyes, so look around. So that would be the orthographic projection, or where we have a near plane and a far plane, and everything between the near plane and the plane is rendered by the computer. Everything outside those two is not rendered. So if something is between the camera lens or the view position and the near plane, it's not rendered. Like you know this in written games, retro games that specifically use this mechanic or anything else that is messed up. You have this walking to the walls to see through them. So if you're very close to a wall, the wall disappears. Then the wall is between the near plane and the position of the camera and is not rendered. Also, if the far plane is pretty near, also with older games, then things in the distance disappear. So this can have flickering in the distance can have two main reasons. One is the level of detail switch, which sometimes is visible if the step is too high. You're switching from a lot of polygons and high detail textures to very few polygons and very not detailed textures. The switch is seen, or you're going beyond the far plane and then you don't see it anymore. Of course, you see a horizon, but that's typically a skybox. With a box or the inside of a circle where you project the texture of sky onto. Yeah, so with the older games, this is specifically a problem because they typically messed up this far plane in that sense that it's really near because you do not have to render a lot, especially if it's in the distance. The more common the games get, the more dark and misty they get. And then the mist is basically a for-free shader operation. And this for-free shader operation just obstructs the view on things that would disappear anyway. So this binary disappearance, like magic, that's hidden by the mist or the layer of grayness or darkness or whatever, that can be easily done with a shader. We'll come to that. Remind me if I forget to talk about it in the Z buffer section, but that's how you basically. I mean, nowadays you just say start mist here and end mist there so that you can't see anything. Most of the game engine. See, I haven't found anywhere you cannot do that. It's a common hardware operation. Okay, so perspective projection is the view frustum, and wait, maybe I have to look at the monitor to the left first. So this near plane, then these side lines and the far plane together make this frustum. And it looks a little bit different because, of course, this angle here, the field of view angle, is a very important parameter. And as you can see, this circle or sphere should be as the box here, but the sphere appears much smaller. So that's because of perspective. Where we get the homogeneous coordinates back. The homogeneous coordinates are used to make farther away objects smaller. It's basically free in a mathematical abstract model. That's so the humans have a field of view of 180 degrees, as you know, rabbits and all those flight animals, not the fight animals, but the flight animals, they have the eyes mostly on the side so that they cannot see sharp and judge the distance of an object, but they can see everything around them. And if they notice something is going on that they don't like, they just take flight. That's the whole idea. Rabbits, horses, and all those things. While predators and birds of prey and those, they have the eyes like humans where you can judge the distance because they have to run, jump, and bite or claw or whatever. On the animal. So the humans have this bird of prey-like view with 100 degrees field of view, but only 120 are actually good enough for clarity. The rest is just context. So you see that something happens somewhere here beside your eyes, but you maybe not even able to know what it is. You have to turn your head. That's the idea. I mean, we can also move the eyes inside our sockets, which, for instance, an owl or an eagle owl cannot. They have to move the head. Why they look so funny? You ever thought about that? You want to learn more about birds? Play Wingspan. We had a podcast episode. Xenia actually did a great pitch for Wingspan. I was nearly pressing the buy button, but the problem was that playing it with the kids in English might be a little bit overdoing it. And I really want to have the Europe edition of it in German. So let's see if I can manage that. Anyway, I got sidetracked. Sorry for the anecdote. Field of view is depending on the setting. So if I go forward, humans have 180 field of view. And if you're sitting in front of a monitor of a TV set, then the TV set or the monitor takes a part of your viewing section into account. And if you're farther away, like from a TV set, then it takes 40 degrees, for instance. While if you're staying just in front of it, like I'm now sitting, or my huge monitor, it's actually rather old, because I don't want to have a good one, because then I look just more into it. It's kind of a hand-egg problem. If you're nearer to the monitor, it takes up 90 degrees, for instance, like mine, more. So the viewing angle is very different. And of course, that impacts the choice of field of view for games. So console games have to be larger than 40 degrees. So like 65 is common, because if you're smaller, if your angle is smaller, then the field of view angle is smaller than the viewing angle, then you feel constrained by looking at it because you only have a small portion of it. While if it's bigger, you have like a window in a virtual world. That's the So 65 is common for console games, and of course for games on the PC, it has to be larger. That's the whole idea. And you can easily see that if you have 65 degrees and cannot change it in a PC game that has the original version on console because of the PC port, then this is very annoying. It's a very cheap port because, then you have the feeling that you only see part of the world. And it doesn't really help if you go back because then everything just gets smaller. Okay, now I know the buttons again. I can pop up again. So the larger the field of view, the more of the game is actually visible. We have here a sample scene. The view with 65 degrees is A. Oh, I love Wingspan. It's called Flügelschlag in German. If you buy it, buy the Oceania expansion. Makes the whole game a lot more balanced. Oh, that's a very good tip. So I can ask, is the German version actually any good? Because sometimes the translation loses of the game. The tip. Yeah, so it's called Flügelschlag. Okay, then field of view, 90 degrees is view B, and as you can see much more. You can see the everything left of the saved cooler. So I picked so many up of them in Fallout 3 and 4, and now I don't know how these things are called. Air blower? No, it's not a air blower. Ventilator? I don't know. Whatever. And the water dispenser on the right-hand side. That's easier. You can see it for full and an additional lamp. Oh, see, thank you very much for suggesting that the German translation is great. So I might definitely chip in. The fan. Oh, yeah, thanks. See, picked so many up in Fallout 3 and 4, and then I don't even remember it's called fan. But I think you get screws and a lot of other stuff, so they're very important, but heavy to carry around. Yeah, that's heavy. Anyway, away from Wingspan and Fallout, back to field of view. If the field of view is too large, like 120 degrees and more, you get a distortion in the image, which is often called the fisheye effect. Very much like these GoPro videos with the ultra wide angle lenses. So they're sometimes great, but not so great for other stuff. And if you're not used to the fisheye lens movement, then yeah, this is also kind of disturbing. So there might be an individual sweet spot, and maybe it's not the one that the developers decided to put in and hard code in the game. So that's an open question. If you complain about the developers putting in a fixed field of view, it's a game mechanic decision, and your individual sweet spot might be somewhere else. I happen to have that sometimes, and then I don't like the game just because it strips my view or something like that. Yeah, but it's a complicated question. As every question. Games, of course. Then you have the aspect ratio of the camera. So it's the ratio between width and height of the camera. So if you have a 1:1, it's a square image. HD TV typically has 16:9. 4K would then have 3840 by 2160 pixels. It's quite a lot of pixels. And the typical TV set years ago would be 1080p, 1920 by 1080. And what was before that, because they didn't have that powerful hardware. When they started with HD TV, it was HD, they called it, not full HD, but HD with 720p, which is typically now reserved for stuff like the Steam Deck or something like that. And if you just multiply lines by rows, you'll see that the processing power for 4K is not 4 times larger, but a lot larger than you need for 720p. And that's also the beauty of the Steam Deck and all the upcoming handhelds, that as the screen is so small, you can actually render everything in a smaller resolution and could theoretically play AAA games on it. Some developers even take the extra step and port them in a way that it's meaningful to play them on a small device. Other common aspect ratios are 16:10, that's typically found on mobile phones, 7:3, like ultra-wide monitors and movies, 29:1, that would also be mostly in cinemas. And unfortunately, games have to decide how to switch between these aspect ratios. If you have programmed games, so one first approach would be just to select something that is already there, or something where you see, okay, that's what we want to play for, like 1920 by 1080, that's typically as a first approach, because 4K is just too much load for a development machine. And then you have to start to deal with all the rest. So game engines like Godot would then allow you to letterbox it, to zoom in, fill it up, and so on and so on. If you have a 3D world, then stuff will be added on the sides. So that's actually pretty good. If you have a 2D world, this might be more of a problem. If the camera is just a look into the world, like on a tile map world or in 3D world, it's not so much of a problem. But on the other hand, it changes the view on the game for the players. So if you have, for instance, one of those curved large it's like playing on an IMAX screen, absolutely. And if you have one of these huge curved monitors and your computer can handle it, like having spent a lot of money on a GTX, what is it currently, 1590? I don't know. I don't order one of those. And you play Need for Speed or something like that, then you can see more. That's the typical idea. You can turn your head and then you can see what's happening outside of the side windows of your car. So you have an advantage over the other people. It changes the gameplay. That's exactly it. You're engineering an experience for the players, then this is not an easy decision. You go to wider or narrower and so on. Okay, then camera movement. These are the camera axes in Blender. So you have pan or yaw, which would rotate the camera around Y. It's like rotating the head, like the owl. Then you have tilt, which is up and down, rotating around X. You have roll, which rotate around Z. That's when the horizon is changing. I wanted to say tilting, but it's not, because tilt is rotating around X. So I'm not using this word. If the horizon is changing, then you roll. If you zoom, then you change the field of view typically. Because going near that, it's called dolly. That's the move along Z. The truck is the move along X, and the pedestal is the move along Y. So these things come from cinema terms. And that's one very fun aspect, which I always come up with in the lecture, but always forget to put in a good example for it. It's called the dolly zoom. I don't know if you know that. So you zoom in, but move out, or the other way around. So you make the field of view larger and move in at the same time, or smaller and move out at the same time. So dolly plus zoom. And this gives very interesting effects. It was very hard to do. Nowadays, you can do it automatically sometimes with the right cameras. But it was very hard to do, and it gave this very strange thing because it changes the perspective of things. You can Google it up and look at it at YouTube for good dolly zoom examples, or if you have one in mind, if you're a cinema enthusiast, then maybe you know dolly zoom and you know a great scene where this happens, and put it in the chat and people can just look at it on YouTube. But please be aware, remove the ability to post URLs here, because there were a lot of URLs where you can make money fast, win a lot, or send money to other countries outside the European Union for I don't know what. Okay. Types of cameras. There is in games, we have different types of cameras. So there are so many viewing angles on cameras. Yeah, so orthographic versus perspective. Field of view, then how to move the cameras, and there are types of cameras which connect to the movement of the cameras. So one type of camera is the fixed camera. You have the same position all the time. That would be the camera from Bomberman or from Pac-Man, where you don't never ever move the camera. Then you have first-person cameras, which are in the perspective of the player. Yeah, you try to put a new URL in here. I'm sorry, that doesn't work. But you can give the title on YouTube, and people can Google it themselves. So first-person cameras are basically set between your eyes, and you walk along. It's not like that. Oops, yeah, that's okay. Okay, I know one of them is in the first Lord of Rings. Okay, I actually didn't watch too much of Lord of Rings, because I'm a huge book fan of Tolkien, and then it was so surprisingly cut down and summarized out a lot of this different stuff. Jaws is the first dolly zoom ever, easily find out. Oh, okay. First dolly zoom Jaws. That should be the one you can find on YouTube. Thank you very much. Yeah, first person cameras move on the top of your head, basically, or here in this area, or nose, or actually between the eyes. So sometimes these first person cameras give you very strange views. Like everybody is much bigger than you. It was also in older games. Sometimes it's completely messed up. Then you have the follow cameras, where the cameras follow an object like a car or an avatar. You have that in tile maps, for instance. So you put the camera on top of the actor or avatar, and then avatar moves, the camera moves, and the world around the avatar moves. And of course, you have the cutscene cameras, where you have cinematic camera movement and positioning, like the end of a level and then zooming out or zooming in or whatever. So you had that a lot in Lara Croft, in the remakes of the Lara Croft Tomb Raider games, where the game camera was a follow camera or third-person camera, and then the cutscenes would basically use the same camera, like flawlessly moving to the start position of the cutscene, and then the game would go on, but removing your control of it. That was very well done. And an example into my mind. There's surely a lot of others. Okay, so how would a follow camera actually work? You just have a wonderful game you'll definitely love when you see my game. I hope it works. Because on an organizational point of view, they did update P5 Chess. They didn't update it for 10 years, so I did not expect that. There was no signs ahead of the road that, listen, we'll update it to a new version, breaking all the old stuff. And now I'm in this weird position that I have to try everything again, which I only did in parts. And I hope it works, actually. Good. And next year, I have to decide if we're still sticking with P5.js. I really want to move to Godot, but some of the stuff is really hard to do in Godot, actually. Very much misusing the game engine for stuff that should not be done in the game engine anyway. So maybe we'll use GL or something. Let's see where this goes. But do not wonder too much. They updated P5.js. And just make sure if you're using the version 2, then let me know, because just put it in comment inside the source code. But currently the main version is still 1 point something, because they released 2.0 and then 2.0.1, and they still call it beta. So also a weird decision, but yeah. They didn't deprecate the old version, which is the common approach. Anyway. Let's not rant on P5.js. It's wonderful software because it saves us a lot of time. So we have the camera behind something. So the avatar is just a box, which is actually not a box, but a sphere, orange sphere. And the coordinates are box X and box C. So Y is fixed. And the camera follows the box, basically. There is the eye coordinate, there is the where to look at coordinate, which is the same coordinate as the box, and the eye coordinate is just behind the box, and look it up with -60, and yeah, then we just paint the sphere. Okay, let's see if we can find that in here. Totally findable in my introduction to orthographic stuff. That would be basic follow camera. I like it, basic follow camera. Now it works, okay? So that would be the basic follow camera. We have to click in there, and there is this wonderful street, which is a sine curve, left and right. There is no way to actually check if it's inside the boxes, so it's just for fun here, and you can move the orange, we call our orange a car, and we can move it in there, and the camera would then follow. As you can see, it's really perspective, so everything is cut down at the end of it, and it's far away to see if there's a real end, but I think there's a real end to it. Yeah, so that would be the classical follow camera. There is an advanced follow camera, which is, I think, on the next slide, and I'll just show you in advance. So if I move and then stop, the camera is like added to the object with a rubber band. So if the object moves far away, you stretch the rubber band, and the same goes for the angle. If I move left, move right, and of course there is easing inside. Easing is very important, make it more fun and more engaging to view it. We can have a lot of fun with just changing the parameters. I have to check, where's my spring follow part? Change for different spring behavior, that's what I wanted. Let's change it to 128. Always good. And this 128. And then we can move the whole thing. And now the rubber band is much more loose. Epic animation, epic game. Thank you very much. I was so lazy making that. Sine line of boxes twice, doubling it in an orange as a card. I could have done better, I have to admit. Anyway, I can also make it more snappy, like going down to 4, for instance, and it automatically reloads. Then it's not really noticeable, but more feel for those people who actually do it. It would match more with the behavior of a platformer, where you do not want to have a linear start, but an ease in and ease out, and that you can do with a follow camera. That's actually pretty cool. How do you do it? It doesn't look easy, but it's actually really easy. I did a lot of that in my master thesis, and then later on I used it in my PhD with automatic rearrangement of graph nodes. And it's the same thing, but on dope, because you have more graph nodes. In this case, you only have two. They're connected by one edge. So the edge would be the look at thingy. C would be the camera. D would be the camera. Then the look at thingy is the rubber band. And what we actually have here is we have the A to look at. We have the A plus O, the difference between A and the position. And we want to go here, but we are here. And the look at is our rubber band, basically. If it's stretched more than this one, the O vector, it's pulling it along. That's the whole idea. So where is it? Spring follow camera is very easy. You just add a part of this vector to C. And the more you add, the faster, the harder the rubber band is. So that's basically it. The vector M from C to A plus O is M equals A plus O minus C. And that would be this vector. And then we just divide it. And the more we divide it, the more relaxed the rubber band gets. Just add it. And at some point, the difference is too small, like here, and we stop it. We say, okay, that's close enough, stop it. So that's just an approximation of the whole thingy. It's not very accurate, but it's good enough. You only have to use something like that to stop the animation, because if it's overstepping, then it's going back. If this epsilon thingy in the distance is too small, and then you would have a camera wiggle or shake you don't want. Okay, so that would be visualization of the whole spring follow camera. So for each frame, we compute the vector M, which is the green one, from the vector C, where we have the camera, to the position where we want to be. And then we move it along this vector, but only for a fraction of it, divided by S. The bigger the S, the smaller the force of the spring. So just a nice little thing. Of course, you can use a log function too, but that would just implement the plain old spring equation. Okay, then what else? We could do an orbit camera, and the fun part of it is that there is already a built-in orbit camera, but we can have the camera rotate automatically, which is absolutely disturbing. So, but it's fun to see that it's absolutely disturbing. It's like tilting the horizon in a VR game. And the camera would orbit around a point, so the eye point, by using cosine and the sine function with a radius of 8. I think it's 120. Yes, radius is 120. Okay, let's take a look at that one. Those two, there should be the orbit camera. Here we are. So orbit camera. So the camera just moves around it, which is absolutely cinematic. Of course, you have ease in, ease out function. That would be awesome. You can easily just plug it over the whole thing, that it's faster and less fast on certain points. That would be cool. And of course, if I click in, then I can move the whole thing, and it has a very distinct feel because you change the view, but you do not change the relative impact of the buttons. So at some point you're just switching the buttons, and now we're going back. Like these racing games where you remote control the cars, where the direction of the car does not impact your steering behavior. It's also really fun. I did a multiplayer game once because we played it a lot, a friend of mine, while doing homework in school. And I redid this game just to have the fun of playing it once again. I don't know where I did exactly do it for. I have no. Yeah. By the way, if you're searching for an internship, we really want to have a redo of that game. So the game as a prototype is there for 2 players. It's a time-based game in Godot, and we're really searching for 1 or 2 students. So it can be either an individual project or a team project where you create this game as a showcase game you can use to showcase what we can do in GSE. It's not too much work in the sense of I did it in 2 days, but of course it's a little bit crappy, not really configurable, but it's a good place to start from. And then we can design more levels and add people to it, like 4 controllers, 2 controllers, sharing controls. There are a lot of options. If you want to do an internship, an internal internship, we're actively searching for people implementing that game for us, where a prototype already exists on game project. Okay, let's close this one. And we're back to the slideshow. Camera shakes. Last year, I thought, oh my God, most people really want camera shakes. And for that, we're in this position where we have this virtual camera. We can easily move it, but what we actually want is we want to make it more natural. So if you move a camera, for instance, I mean, nowadays the camera shake is removed by a lot of software libraries, but if you take a look at the older movies like the Super 8 movies or those that have no shake countermeasures in there, optical or digital, then this is huge fun to see how the camera actually moves. It's like these kids' birthday party movies the parents typically took. Nowadays, most of the camera shaking is computed out of the camera view. It works, but we want to still have some camera shake inside there. We have to model it. And shaking is basically a signal that moves between random amplitude. We shake it in 2 directions, Y and X. We can easily let aside Z for now because the forward movement is not so bad. And we also don't want to roll the camera around C, but just move it up, down, left, and right. So X and Y. And what we need is a number of amplitudes from a frequency. So we want to shake and then ease it out a little bit because you typically move and then try to move it back to the center. Try to move it back to the center. Fast in, slow out, basically. So what we actually want to do is we want to shake in X and Y direction with different functions. So we have 2 different amplitudes and then lurk between those amplitudes. So it's not so bad. On the one hand, we have the pointer. We have the re-roll camera shake, which basically gives us a camera shake. We have 200 points in there. And for each of the points, the amplitudes, we push a random number between -1 and 1. So add random times 2 minus 1 is a random number between -1 and 1. And we push 1 for X and 1 for Y. So we have a list of 200 numbers. As you might recall, JavaScript lists, arrays are behaving like stacks if you use push. So yeah, makes things a lot easier if one data structure can do all. And then we lurk between 2 amplitudes. So we are in the current segment and we want to have current segment +1 and then the position times the segments minus current segment and just lurk between them. And easing out is getting towards this position. We're using the sprint follow basic. Okay, we're using delta time for that and re-roll the shake after the shake has ended. So if the segments are too much, then we re-roll the camera shake here. And well, yeah, that's the idea. Actually work. I put in here that on enter, where on enter camera shake on is true. Here. So we have the classical follow camera here. And if I hit enter, then we have the camera shake. I'm a little bit overdoing it, as you can see. Of course, this is configurable. We just have to find it. Lerp, shake, current segment plus, that current floor position. -1 and 1, there should be some street length, street width. Yeah, that's bad. I don't find it right now. The shake function should somewhere create vector in draw. Maybe it's in draw. Okay, and here it has the camera shake vector and it's just the raw vector. Basically add something like past half and half and half, and then it should shake that. Let's see if that's true. Yeah, only shakes half. Interestingly enough, the box seems to move differently. Then y times 2 minus 1. Because, thank you for the question, I overlooked it. Y times 2 minus 1, because random gives us a random number between 0 and 1. And that would just mean that we go up. Like between 0 and 1, what we also want to do is we want to go up and down. So we need to move up and down. And typically that would do something like between minus 1 and 1. Because then we can just multiply it by 2, because then we know the maximum up amplitudes and the minimum amplitude minus 2 and 2. So that's why we normalize it in both directions. That's a convenience thing, basically. If you normalize everything, it's great. If you need both directions, you do not normalize, but put it in between minus 1 and 1. But there are question, by the way. What? Okay, you can fool around with the camera shake wherever you want. Have fun with it, make it more human. I actually used some online links where I tried to get some input on how to set up the function, because it did not look very human. What I also wanted to do, if you take a look at the slide, there's a skip slide in there, which is a to-do for me. I actually wanted to have the camera shake modeled based on human-like function. So that is typically possible. We do that in PCG, in procedural generated content, but I didn't find the time to do that yet, as I have to redo everything anyway for the next semester. This is my reminder to do it next semester. But there are many ways to create a shake function. And speaking of the shake function, this is optional for exercise 06. So we have an unfinished sketch called bounded camera. You can find it. You can sketch bounded camera. You can basically move the avatar in 3D, and the playing field is the yellow box. And the whole idea would be that the camera would only follow up to the yellow box, and then the camera would stop. There are basically two things you can do. One group of submissions was always that the camera would just stop and would not update the view or the look at vector. Another group of submissions would then look after the avatar, slowly moving out. And optional, you can use the camera shake functions, let the camera shake when the avatar hits the boundary. You can but move on with the avatar, just stop the camera. That would bound the camera in a certain way. That's the idea of a bounded camera. So that's exercise 6, to get your hands dirty with the whole. You can any questions for exercise 6? Please post them. I'll look at it faster than the last time and give you some input on that. Okay. What I have left from this part here is, as far as I remember, mouse here. Yeah, that's a very good point also to talk about the speed run. So 2 people already finished the speed run at the beginning of the week, and the date is tomorrow, 10th of May, to submit the speed run. So if you want to do the speed run, if one person more does the speed run, everybody gets extra points. So if you don't want to do the speed run, at least motivate your colleagues, one of your colleagues to do that, then everybody gets points. And just submit it until the end of tomorrow. Like a bad movie maybe is. Should already be done. Awesome, great. I didn't check in Moodle. I wanted to check yesterday, but unfortunately there was Moodle downtime because they have to update it, and like nobody works in 8 in the morning, they just stopped it working at 8. You can whatever. Okay, moving on with the cameras. If you have stereoscopic cameras, which means that you have 2 cameras, like for each I1, you can create ER and AR things. You can create the sensation of depth by stereoscopy, and you have typically 2 cameras with the same setting, basically create 2 images. That's the great idea. And the 2 images slightly differ, and that creates this impression of 3D. Output options would be the anaglyph, which is a rendering in two different colors. So, and then you put on these glasses, red and green, or cyan and magenta. I don't know. There are many different ways to do that. And then one eye sees only this color and the other one sees only this color. And then you split up the images so that works typically very well. You can interlace it and the device then has to de-interlace it. You can render alternatively left and right. And then the device displays it left and right, or you have something like shutter glasses that side-by-side rendering, render left image and right image side by side, or top and bottom. That would be the typical options for rendering out of Blender. So nowadays you typically just render it in a format that the MetaQuest headset understands, because most of the competitors are not as accessible that way. I wouldn't say that the MetaQuest is accessible, but the others are even less accessible. So that'd be side by side. There is a slight difference here in the left corner, for instance. You can see the picture here has a slightly different content compared to here, and not longer actually, not a lot. So it's not a lot of difference, of course, depending on the scene. That would be the anaglyph. There you can see the difference more easily because you have the pictures lying over each other. So the object moves a little bit to the left and to the right. Not longer. Yeah. You can do that in Blender. You can do that in Babylon.js with WebXR. You can even do that in P5.js with WebXR. But I doubt this is still working after the update because it was not working perfectly in advance of the update. So the update most likely didn't make it any better. Not longer. And for the rest of our few minutes, we'll go into what we did not cover. So we have pixels that have a color with shading and materials. Not longer. The front-facing facets are rendered. If not, they are being called for being outside the view frustum, so beyond the far plane or not longer near plane. So we did not cover Z buffering. That's very important. We take a look at it and we didn't cover anti-aliasing. Not longer. Z buffering, that's also the thing where I had to remember the mist. I remember that I had to remember something. Great. That's the first step. So what you basically do, you take a look at the objects and then you render the samples. Like later, remember, you render the samples and then you have to store the samples. Not long. What you do not do is following a ray from the camera towards the object and intersect the object. That's not longer. What you do. That's what you do in ray tracing, but not in rendering. So real-time rendering in games does not do that. Ray tracing, ray casting does that. Two different approaches to it will not longer friends with that. And for rendering, real-time rendering, you have to render everything that is inside, even if it's obstructed. Not longer. You render the sample and put it in a Z buffer. And Z buffer it's called because it also stores the Z value. So how far is the sample away from the camera? And then if you have another sample and it's nearer to the camera, you can overwrite the Z buffer. And at the end of the day, your picture would be in the Z buffer. That's the whole idea. So also the tricks with having semi-transparent textures and everything, not longer done in the Z buffer. Then you have to not render it, but store it in the Z buffer, and then the final step, combine everything. That was very, very demanding for the graphics card years ago. Nowadays, with the programmer shader render pipelines and the shaders, that's done in a neck of seconds. That's not too much of a problem. Now, you do not have to do extra rendering. So that's the benefit. You have just the extra step of combining pixels, and that's exactly what shader are good at. Not longer. The Z buffer, you only overwrite if it's nearer to the camera. The harder Z buffer is store everything and then combine it in the final step. That would be a depiction of the whole thing. You have green ray from the eye, from the top, and the blue plane is rendered first. So you put the blue pixel in there, but then you render the red plane after that, and it overwrites the blue pixel. Not longer. Of course, how big needs the Z buffer to be? It needs to be as big as the screen you render, like HD, it's 1920 by 1080, or in not longer HD. In HD, it's 720 by whatever. In Full HD, it's 1080, and 2160p is then 4K. So The bigger the picture, the bigger the C buffer. Not longer. Anti-aliasing makes it even worse. Okay, why would we need anti-aliasing? Everybody knows we need it desperately because otherwise it looks crappy. But why does it look crappy? So not longer. Common older screens, the pixels could be seen. So that's the constraint of it. Not longer. Pixels are big enough that you can see them with the bare eye. Something like that happens. Not longer. You can only draw those pixels. Not longer. See the pixel with the naked eye, then these lines get jagged. Not longer. Not longer. Effect completely disappears if the pixels are small enough. For instance, if you have not longer iPhone and you render on this small screen with 4K and have pixels per inch density of more than 300, 400, then you don't need any aliasing. That's pretty cool. You have less screen pixels or a bigger screen with the same amount of screen pixels, then the pixel density drops below 300 and then you start seeing those jagging. Then we need anti-aliasing. Not longer. For instance, I have now this 20-inch monitor in front of me with 4K and it looks not longer. I have a 13-inch monitor just beside me from a new notebook, which also has 4K, and there I don't need anti-aliasing. Not at all. Not on the fonts, not on the games. If they can be rendered in 4K, that's great. I don't need anti-aliasing. So it's a problem of pixels that can be seen. Most likely, it's easy to solve it if we find screens that have a larger pixel density. As a hypothesis, we don't have it yet. And some people still need it even for 400 and more pixels. So the rasterization of those samples is, in this case, we have white, green, and blue, for instance, and that would be our C buffer. And we have to decide where we sample our color. For instance, we sample the color the sampling would be in the center, like here. Then this would be a blue pixel. We have the center of green, then it's a green pixel. We have the center white, then it's a white pixel. If we do anti-aliasing, we see that part of the pixel, blue, part is green, and part is white, then it comes up with that color. Then the jaggies are gone. Looks a little bit washed out, but much better than actually with these hard cuts. That's the whole idea of anti-aliasing, and what actually works great is if you do oversampling or super sampling. That's also what most common algorithms do. So you take more than one per pixel. So let's go back. Instead of saying we just take the green one for this one, we take, for instance, one here, one here, one here, and one here. And then based on the different samples, we create this color here. We already have a great anti-aliasing thing. So what's the downside? The downside is that we do not have to render one picture with 1920 by 1080 pixels, but we have to render 5 pictures of that size. And as you know, this would mean that for 30 frames, we need to render 150 frames, which is a little bit prohibitive. So we need a better approach. So another approach would be to render twice the resolution in X and Y to have 4 samples per screen pixel. That's not 150 anymore, but just 120. Yeah, does make it better, but not much. And what you can also do, you can do an accumulation buffer, renders 4 images, each with an offset of half a screen pixel. And then it results in 4 samples per screen pixel. And then you can use this accumulation buffer for motion blur or depth of field effects. We have spam. I like it. What I can. Yes. The spam. Yes. Okay. To OBS wasn't possible years ago, so great. I like it. Out the spammers. So super sampling is computationally very demanding, and we have different sampling schemes. So the worst one is the one in the center, one sample. We have a lot of jaggies. We have 1 times 2 samples, either horizontal or 2 times 1 samples, vertical and horizontal, and it helps with some it helps with assay lines. Like here, these lines are a little bit better, but these are not. And here, these lines are a little bit better, but this one is still a lot of jaggies. Then having 5, that would be my approach with the 5. Then you have much better, but more washed out thingies. The cool part is that you can share this pixel assay. So with the others, like this pixel up here, this pixel here, and this pixel here. So you can render this one for 4 pixels. Effectively, it should be like a little bit more than assay. Yeah, if you do it that way. And then you have the 2x2 grid, which also gives great examples, less washed out. Then there is the rotated grid super sampling here, also great 4x4 checker, and you can go down to super sampling with 8x8, so that put 64 images rendered. You really want to do that, maybe for a static image or something like that, or if you want to pre-render a movie, a cutscene, then this would be something, but it's rather prohibitive for real-time rendering. So MSAA, you might read that in several config options is more than 1 sample per pixel, but in a single pass, and sharing the computations among samples, like the incircs, for instance, where you also take out the borders. It's less demanding computation, and the number in front of it gives you the number of samples, like 4 times MSAA used for samples. You can use temporal anti-aliasing. So you have the information from the last frame. If you store it, it just takes the C buffer. So on C buffer from the last frame. Then you use samples from the last frame to anti-alias the current frame. That's information you already have. So you don't have to recompute it. That's pretty cool. Otherwise, if there is a lot of motion, then of course you have a lot of blur, but maybe this is an effect that helps with the motion blur. For it, MFAA, multi-frame anti-aliasing, and EXAA is temporal X anti-aliasing. I don't know. As always, NVIDIA is making extra points with the software they have. They make pretty good software and drivers, and they also make up pretty good names which do not match the names of the others. So nowadays, you typically use machine learning for the whole thing. So we have the image generation thingies, so it make up pixels. You can also make up anti-aliasing for pixels. That's actually cool. And that's also what AMD does, but not called DLSS, but it's called FSA. I always forgot it. I don't know. But what they basically do is you render a picture in any resolution that is near to that what you want. Let's say you have a full HD screen. You don't have the power to actually render it full HD, so you use a slightly less good resolution, but then you use machine learning to upscale it to something that is far more than full HD, like 4K. And then you scale it back, and that's the anti-aliasing step. And then you have an anti-aliased, upgraded picture. That's the whole idea. So what can actually go wrong? Get lost, of course. But what they do is typically train those models that come either with the game or with the driver on 60K anti-aliased ground truth pixels that NVIDIA generates from the games. It's a service from NVIDIA and sort of thingy. As I said, AMD does the same thing. They start later and are not so sophisticated because they did not invest so much into software. It's just a question of time to go. DLSS2 is already outdated. Not sure. I have to look it up. NVIDIA DLSS. Oh, it's DLSS 4 already. Yes. And there's a button by GeForce, of course. And if you take a look at it, then you can actually see you can see the difference between those, and it actually looks nice to play. It's fast enough that you don't have to drop the frames. It reduces the load on the computer, and it makes up information that has not been there. If the information is not game relevant, that's pretty cool. If it's just eye candy, if they're making up information that is not in your game, that's bad. like the 6th and 7th finger on the avatars, or an additional hat or something like that. But they are rather in control of the whole algorithm, so that it does not happen. Steam Deck also uses that a lot. As I said, it's not extremely powerful, and you can render it at a smaller resolution. As I said, one of the benefits, it's very much like NVIDIA, where the driver sets the config options that are appropriate for your computer, and then you can fool around from a working state. The same does Valve for you with the Steam Deck. They configure everything, like you play whatever Hogwarts Legacy, and then they say it works with these things, and then you can turn it up and do some frames, right? Green some frames, they give you a working version. As I said, this upscaling, resampling, as I said, learning is in there. As I said. Okay, there are many techniques to do that. For instance, there's checkerboard rendering, where only half of the pixels are rendered. That's the approach they did with the PS4. Actually do 4K rendering, and you also can use that for anti-aliasing. So that's a lot of different. Okay, so that's what I actually brought today. I know I'm much faster when I'm talking to the camera on stream than I'm in the lecture hall. That's one of the benefits. If I'm too fast, then you can go back on the recording and take a look at it. I will upload the recording after some slight editing. I want to remove some ads and assets, like my screenshot of my desktop. From the video, and then upload it to YouTube and to our university servers. Watch on YouTube for convenience or for privacy, of course you can. Our own cloud servers. That I'm talking that long that if there are additional questions, they would appear now in the chat. Thank you very much for watching. Also those that watch the recording, please do not forget that within a week you have to answer those small questions to get the experience points for watching it. To level up to a positive grade, how gamified are we? Awesome. And thanks for being with me. Thanks for posting the great questions and the examples for the Dolly Zoom. And I'll see you next week, also in stream, unfortunately. Why? Because we have the board game and sustainability game jam going on. So if you're still in need of a block lecture and you have time off next Thursday and Friday, join in there. There's also a second batch with another game jam. You can choose between two of them. Second one has free pizza. First one not. Okay, then. Thank you very much. Have a great weekend and bye.